All right, so we have been talking about combustion. That's leading up to being able to apply the first law for a chemically reacting system. And before we get to the first law, we're going to talk about how we handle the enthalpy. So we're going to put things in terms of H bar. So that's on a per mole basis. And the reason that we're putting things on a per mole basis is because we're going to have this beautiful balanced chemical reaction where the coefficients in front of each of those terms represents the number of moles. So it's just useful to put things on a per mole basis. Now you'll note that we've got 1, 2, 3 terms here. Why is it more complex? And the reason is because up until this point, we've been concerned with changes in energy for processes in which the substances at the beginning of that process and end of that process are exactly the same. So for example, you've got gas A and gas B, they go through some sort of process, and as long as there's no chemical reaction, you end up with gas A and gas B. Now when you apply the first law to this particular process, you'd be calculating changes in enthalpy for gas A and gas B. Now, say you look up the H values for gas A. Well, gas A, the thermodynamic tables, they have chosen 0 Kelvin as their reference point. So they said, okay, well, at 0 Kelvin for gas A, H bar, U bar, S bar, or S naught bar, all of those are equal to 0. All right, great. So I calculate my change in enthalpy between, state 1 and state 2, and then I plug into the first law. Gas B, when I look up in the thermodynamic tables, they have decided to choose an arbitrary reference point of 0 degrees Celsius. Okay, awesome. And that's fine. So that means that at 0 degrees Celsius, H bar, U bar, S naught bar, those are all chosen to be 0, and then they build up their table from there. But that's fine. I'm looking at my enthalpy change between state 1 and state 2. So because I'm looking at the change, I can still combine that in the first law, and it's not going to mess anything up because they're all sort of normalized to their own individual reference point. Now that's not going to be the case if I have gas A and gas B. There's some sort of chemical reaction, and now I'm ending up with gas C, D, and E. I can't look at the change in enthalpy for gas A because, well, I got gas A in my reactants, but not in my products. Same thing with gas B. Same thing with C and D and E. I don't have any C, D, and E in my reactants. So what I need to do is I just need to make sure that all of those products and reactants are normalized to the same reference state, the same temperature and pressure. And our standard reference state is defined as 298 Kelvin and 1 atm. That's our arbitrary choice, okay? It's just a convenient choice. So let's look at this enthalpy equation, or this H bar equation. So I've got the first term, got a H and a bar over the top, a little naught, a little subscript F. This is my enthalpy of formation. So it's found in A25 and A25E. This is the energy that's absorbed or released when a compound is formed from its individual elements at standard reference temperature and pressure. You'll see that some of them had negative values, some of them are positive, some of them are 0, and that just means that it's a stable element, meaning that it's stable at standard reference state. So stable elements are assigned a value of 0 for their enthalpy of formation. All right, now we're looking at the H bar at T ref. So this is the H bar evaluated at 298 Kelvin, the standard reference temperature. And the place, and I can also shorthand this as H naught bar, okay, instead of writing with like T ref, with just the understanding that it's evaluated at 298. So I can find these for various gases in table A23. Now you remember from the combustion intro, when we get our balanced equation, your reactant or your products, you've typically got carbon dioxide, water, and nitrogen. Sometimes if you got excess oxygen, you got oxygen there. So all 4 of those things are found in A23, conveniently enough, or A23E if you're in English units. So I'm looking at 298, and I can pull off, say, the H bar value for carbon dioxide at 298. It's 9,364 kilojoules per kilomole. No problem. And then, of course, that other H bar at T, that's the temperature at whatever temperature that your product or reactant is at. So I'm finding that in A23. If the temperature my product or reactant is at 260 Kelvin, great, just pull it right off the table. If it's at 300, pull it off the table. 220, pull it off the table. No problem. I just need to know to pull it off the table. So now I'm going to kind of put a pin on that H bar stuff, and I'm just going to come back to my first law. So let's look at the case where I've got an open system. So I've got stuff being supplied and stuff coming out. Reactants being supplied, products coming out of my combustion chamber. I'm going to put things in terms of moles. So you'll see this equation looks really familiar, except I've got, instead of like H plus kinetic energy plus potential energy, I've got a bar over each of those. And I replaced my m dot, my mass flow rate, with n dot. So the n dot is the molar flow rate. So kilomoles per second. And of course my H bar, my kinetic energy bar, my potential energy bar, those are all kilojoules per kilomole. So it's equivalent to putting m dot times H plus kinetic energy plus potential energy with no bar. All right, so my units, for the entire equation is kilojoules per second. Now, if I make the assumption that this is all steady flow, meaning that I'm supplying those reactants at the same rate over time, and the products are coming out at the same rate over time, don't have any work for this combustion chamber, kinetic and potential energy changes are 0, then this is the guy that I get. So the first term with a little e, the stuff that's coming out at the exit, that's my products. The stuff that's coming in at the inlet, those are my reactants. Okay, it's often convenient to express things per kilomole of fuel, per 1 kilomole of fuel. So what I'm going to do is I'm just going to divide through by the molar flow rate of the fuel itself. Okay, so if I do that, then this is what I've got. And I've replaced that E and I with products and reactants, you see, and I've divided through by the n dot of the fuel. Now I'm going to kind of make this a little bit prettier, and I'm going to say that the n dot over the n dot of the fuel for the products is just n with a little subscript p. Same thing with the reactants. And what that little n with a subscript p is the number of kilomoles of my product over the number of kilomoles or per kilomole of fuel. And why is that convenient? Well, that is convenient because I have a balanced equation that is essentially written like that. So if I've got a hydrocarbon plus a theoretical amount of air, or maybe not a theoretical amount of air, maybe, excess air, whatever, that X, Y, and Z, those are written in terms of kilomole of product per kilomole of fuel, per 1 kilomole of fuel, because I've got 1 in front of that hydrocarbon. That's the, implied, not subscript, but coefficient in front of that term. So X, it's the number of kilomoles of CO2 per 1 kilomole of my hydrocarbon fuel. And that would be the little N with a little subscript P, where the product is specifically carbon dioxide. And so now I'm ready to bring in that information that we talked about at the beginning, the H bar definition. So if I do that, I'm just replacing that at H bar with my my better definition for H bar that I have to do since I've got a chemically reacting system. So the H bar is replaced by the enthalpy of formation plus the enthalpy, the H bar at whatever temperature that my product or reactant is at, minus the enthalpy, the H bar at standard reference state for my product or my reactant. Okay, so there's a lot of stuff there. It'll look a little bit better, or make a little bit more sense when we actually start using this. But all right, for our closed system, very similar derivation. We're not going to go through the derivation here, but it's a similar derivation. You're making the same assumptions. Kinetic and potential energy changes are 0. You don't have any work. So this is the equation that you've got. And I've still written things in terms of NP and NR, number of kilomoles of product per kilomole of fuel, same thing for the reactant. And now what I'm going to do is I'm going to replace that U bar by the definition for U bar. So just like U equals H plus PV, I can say U bar is equal to H bar plus PV bar. And that V bar is the specific volume on a per mole basis. So it would be like meters cubed per kilomole. All right, so I've done that now. And the other thing I'm going to do is if I assume that my products and reactants behave as ideal gases, and that's something we often do. Your products are coming out probably a very high temperature after the combustion process. You'd expect that temperature to be really high. And so it's not so much of a stretch of the imagination to think these things are behaving as an ideal gas or in that ideal gas range. And for example, your gas or your fuel, typically that's in a gas form. Your atmospheric air, if it's being combusted with atmospheric air, not so much of a stretch of the imagination to model that as an ideal gas. So if I apply my ideal gas law and I express P V bar as R bar T, and then I bring in the definition for H bar, where I take into consideration that this is the enthalpy of formation plus H bar at whatever temperature that my product or reactant is at, minus H bar at standard reference state. This is the final equation that I get. So there's a lot of information here. Oh, and that's not at the very, very bottom. I'm sorry, that's not Q dot, that's just Q. So I'll make a note in the video, but it's Q, not Q dot. But that would be in kilojoules per kilomole of fuel. And we will work some problems the next time that we meet so that these equations become a little bit more useful or a little bit easier to work with. So, all right, well, thank you very much for watching. Let me know if you have any questions.